Hello everyone. So this is second lecture on quantum physics, and in today's lecture we will continue our discussion on energy of photon, and we will discuss about photoelectric effect in today's session. Okay, so I hope you have completed first lecture because that sets the foundation for further concepts of this particular quantum physics. Okay, and in today's session we will discuss about photoelectric effect, and the prerequisite for this photoelectric effect is understanding of photon and its how to calculate the energy of photon. Okay, so let's begin today's session. So our today's topic will be photoelectric effect. Okay, fine. So just to review, just you can say recap of previous session. So we discussed about energy of photon, that was hc by lambda, or we can write it as h into mu, or we can write it as h cut into w. And in terms of lambda in nanometers and angstrom, we can write like this. And in terms of angstrom, we can write like this. Okay. So please revise this formula because this will help you in the mathematical, or you can say numericals mainly. For concept art, we will use different method. Okay, so let's start. So we are discussing photoelectric effect. Okay, so there was a photoelectric experiment which was you can say performed by not only Einstein but some other scientists also. But this effect is you can say theory, which is which was given by Albert Einstein. But photoelectric experiment was like you take a discharge tube, then a cathode anode, and then they are connected to terminal of battery. So that was you can say an experimental result. That was an experimental concept, and here we are going to discuss about the main effect, that is photoelectric. Okay, first of all, as the you can see from the name, it is made of photo and electric. Okay, so it is actually called as photon electron effect. So it is you can say a relation, or you can say there is something which between photon and electron in this particular effect. It plays a very important role. So we are going to discuss this particular photon electron effect. Okay, so photon and electron effect, it is also important. Now see. Okay, so actually what happens in photoelectric effect, there is a metallic surface. Okay, on that metallic surface, uh, beam of light, or you can say array of light incidents, which consists of photons. And then you can say that photon carries an energy, which we discussed as sc by lambda. And now this particular metal surface also possesses an special type of energy which is called work function. And then you can say there is a relation between them, that energy of photon and the work function. And depending on that, uh, it is decided that whether electronic emission will happen or not, because it is actually photon electron effect. It means photon is incidented, and then on the basis of the conditions, or the you can say requirement, electron ejection is decided. Okay, actually what happens in the inside the metallic surface, that photon and electron collides. There is also loss of energy in collision. Then finally, the electron which is ejected out, that electron possesses a something, you can say some kinetic energy. Okay, so let's discuss about it using a simple illustration. So suppose this is a metallic surface. Okay, and this metallic surface, obviously consists of electrons. Okay. Now a ray of light is incidented, and this ray of light has photons, and now this photon carries energy that is called as EP, and the energy associated with this metallic surface, that energy is called as work function. We will discuss about it. That is denoted by phi. Okay. Now this EP and this phi, between them, you can say settlement is there, and that settlement, when it when this particular settlements become equal to each other, like EP says EP is equals to 5, then no electron emission occurs. Okay, actually, but if this EP is greater than 5, if EP is less than 5, so different conditions are you can say formed. So a simple, we can illustrate it in this way, that photons are incidented on this metallic surface, then photon electron, or you can say collision occurs, and finally electrons are ejected out, and this phenomenon is called photoelectric effect, that is photon electron effect. Photon comes, photon, and then electron and photon collides, then finally electron ejection occurs. Okay, so this is your you can say a broad idea of photoelectric effect. And now we will discuss about it in detail. First, we will discuss about its parameters, its terms, that is work function and associated terms, and then we will come to this particular uh, effect and its conditions, and most important, photoelectric equation. Okay. First of all, we will discuss about a term called as work function. First of all, its denotation is by phi. Okay. It is a mathematical you can say symbol, that is phi, and through this we denote work function. Okay, and this work function is actually a property of metal. It's a property of metal. It's a property of metal. First, you have to understand it's a property of metal, and if you just change the metal, then the only work function changes. Otherwise, changing frequency or changing any other parameters does not alter it. It is actually a constant for a particular metal. For a particular metal, it is a constant. If you change from metal from suppose you take aluminium, and you then changes to another one like iron, suppose, then work function changes. But in the for a same metal, work function is fixed because it is a property of metal. Now, how it is an energy? So it is actually a minimum energy. It is the minimum required energy for photoelectric emission. Okay, so for this photoelectric emission, the minimum amount of energy that is being required, that is only the work function. So we said that work function is actually energy only. It's, you can say, dimensionally also it is equal, you can say equals to energy's dimension, and also it is an energy only. It is a minimum amount of energy. You can say minimum required energy for photoelectric emission. Okay, so we write that if that photon is coming with energy EP, and that energy is less than 5, then you say what happens. Three conditions are there. If this particular EP equals to 5, then what happens? And then when this EP is greater than 5, then what happens? Okay, so these are the three conditions, three possible conditions for this you can say a relation between this particular energy of photon and the work function of the metal. Now, as we discussed that what is actually work function, what is the essence of work function, that is a minimum amount of energy which has been required for photoelectric emission. But if the photon is coming with an energy less than that minimum energy, because that is the minimum energy, that is the bare minimum requirement for photoelectric emission. But if the energy of that photon is, it doesn't match up with the work function, and even it is lesser than that you can say work function, then there will be no photoelectric emission. Thus you see very logically that photoelectric emission we need a minimum amount of energy, and that minimum amount of energy should be equals to work function of that metal. But if that energy is less than that work function, then there is no any possibility of photoelectric emission. Okay, so here there will be no photoelectric emission. Now second condition, when this energy is equals to the work function of the metal. Now you see work function is the minimum amount of energy, and now this particular photon is coming with the energy that equals to the work function of the metal. So here we will have photoelectric emission, but there is a you can say condition with this, or you can say a point which is uh, important. That is, photoelectric emission will occur, but with no kinetic energy. Means just electron will be ejected out, just with the no kinetic energy. With kinetic energy equals to 0. Okay. Now, when EP is greater than 5, then you see, suppose energy of photon is 15 electron volt, and your phi is 10 electron volt, then no issues. What's the issue then? We need a minimum 10 electron volt as per the, you can see if this is 10 and this is 15, then we need a minimum of 10 electron volt for photoelectric emission. So photoelectric emission will occur surely, because energy of photon is greater than 5, and actually the difference is 5 electron volt. So the here also photoelectric emission will occur, but here we will have a kinetic energy of that electron, and that kinetic energy will be the difference of this. Okay, because you see phi energy you can say uh, the phi amount of energy is being used to just you can initiate the process of photoelectric emission, but the difference which is there between EP and phi, that produces, or you can say that leads to the what you say kinetic energy, or you can say that leads to the electron photoelectric emission with an electron with an definite kinetic energy. So here photoelectric emission will occur, emission, and with kinetic energy, fine. So from here we are on the our way to get the photoelectric, or you can say photoelectric Einstein's photoelectric equation. What's it? So that is maximum kinetic energy equals, why it is maximum we'll discuss, equals to energy of photon minus work function of the photon. We will discuss more on work function. Have a patience. This is just an intro to the photoelectric equation. We will have a more discussion on this. So kinetic energy, maximum kinetic energy is equals to EP minus phi. And this is called photoelectric equation. Okay. Now why maximum kinetic energy? Because when electron, you can see this. You can see this figure. Suppose this is metal, metallic surface. It is electrons are there, protons are coming, electron emission is occurring. No issues. But this electron will, or you can say it can just eject out also, or you can say it can eject out with no kinetic energy also, or with some kinetic energy also. That is also, these are two possible cases. But according to photoelectric equation, or what we wrote, the maximum kinetic energy will be that H, you can say EP minus phi actually. But the possible values of kinetic energy, as we said that there is also an inner collision between photon and electron. So that kinetic energy will range from 0 to the k max. See, two things are there. One is collision factor, okay, and second one is your condition, whether it is EP is equals to 5 or EP greater than 5. So this kinetic energy is in this range 0 to k max. If I'm writing kinetic energy, so it belongs to a range of 0 to k max. Okay, it can be 0 also, it can be k max also, it can be between them also, and that sometimes it is also in hurry we write k is equals to kinetic energy equal to EP minus 2. This is wrong. This is not photoelectric equation. Photoelectric equation deals with the maximum kinetic energy. Deals with the relation of between maximum kinetic energy of photon and the work function of the matter. So this is not actually, the actual is your K maximum is equals to EP minus. Fine. Okay. Now again one thing you have to note here, that this ejection of electron, photoelectron is, photoelectron means electron here associated. We are naming it a special name, photoelectron. Here we'll also name a current that will come, that is called photocurrent, which is produced due to this particular effect. That is why so it is used with a prefix photo. Ejection of photoelectron is actually instantaneous. It will not take so much time that we are discussing that photon will come, then a collision occurs. It's a very instantaneous process within seconds, within a fraction of seconds. Okay. Now, let us discuss more on work function. So work function denoted by phi. Since it is an energy, we can write it as h into and frequency, that is nu naught. We cannot write here nu because it is a different kind of energy. It is work function only, and it is different kind of energy than the energy of photon. So we will use a different symbol, that is mu naught. What is this mu naught? This mu naught is called as threshold frequency. Okay, so let's discuss this threshold frequency first. So threshold frequency, so it is actually the minimum amount of, not amount, wait, it is also wait, the minimum frequency required for photoelectric emission. Because you see in the equation, for photoelectric emission what we need, a minimum amount of energy that is equals to work function. So hence here you can see h is a Planck constant, so we can write it as a directly proportional to mu naught. So this mu naught will behave as same as the work function of the metal behaves. So it will be a minimum frequency, it will be the minimum frequency, or you can say minimum frequency of incidented light. In more specific mode, you can say clear way, there is a minimum frequency of incidented light or incidented photon that is required for actually photoelectric emission. That is a minimum amount of frequency, that is called threshold frequency, denoted by mu naught. Okay, again we can write this phi as h mu naught, and also we can write it as hc by lambda. Now again h and c both are the constants, so we can write this phi as inversely proportional to lambda naught, and this lambda naught is actually called as threshold wavelength. Now here behavior of this particular wave work function and this lambda naught will be opposite to each other. Means we are saying that this is the minimum amount of energy, so we will write here maximum wavelength required of incidented light required for the process. Okay, so see, let us define it. for a just sake of completion. So threshold wavelength, so maximum wavelength of incidented light or photon required for photoelectric emission. Fine, this is not a well lambda naught. So this was your threshold frequency and threshold wavelength. Now we will come again to the photoelectric equation and we will discuss it in terms of these two new, you can say, quantity which we have defined. Okay, see, you can write K maximum as EP minus 5. We can write EP as H into nu, and this uh, frequency in terms of wavelength, frequency only, threshold frequency, because here you are taking frequency of the incidented, you can say, light. So here we will take also the frequency of, or we can say threshold frequency. We cannot take here wavelength. Okay, so it will be H into nu minus nu naught. Fine, this can be the interpretation of it. Again, we can write it in terms of wavelength also. Let us discuss it in terms of wavelength. First of all, you can see from here also that for photoelectric emission you need a minimum, this frequency should be, you can say, greater than, okay, equals to mu naught for photoelectronic emission. Fine, this mu should be greater than equal to mu naught, and again mu will be equal to mu naught, then k max will be 0, and if mu is greater than mu naught, then we have the definite value of kinetic energy, maximum kinetic energy. Okay, now in terms of wavelength we will discuss. So let's discuss in terms of wavelength. So k max is equals to EP minus 5, or you can write it as hc by lambda minus hc by lambda naught. Now just take sc as common, 1 by lambda minus 1 by lambda naught. Now what you have to understand, that we are in the case of 1 by lambda and 1 by lambda. Now this what you say, lambda naught, okay, should be greater than equal to lambda, because if this is the condition, then what you can say that 1 by lambda naught, 1 by lambda naught will be less than, if this is the condition, then write 1 by lambda naught will be less than equals to 1 by lambda. Yes or no? And this actually we need for photoelectric emission, so we can write this as this term, that lambda not greater than equal to lambda for photoelectric equation, equation, I said emission. Okay, so this is the condition between threshold wavelength and your incidented light, wavelength of incidented light. Okay, so this was your in terms of wavelength. Okay, now we will have a more discussion on this particular parameter, maximum kinetic energy. So electron associated in this experiment is called as photoelectric. Current association, current associated in this experiment will be called as photocurrent. Okay. These are the two things. Now we will discuss about number of photons per unit time. Means we will define some things here to just get this particular dNp by dt. Fine. So let's discuss on this. Let's discuss. So we will, let's suppose source is of power p watt and photon light source obviously coming is with a photon coming is with energy E. So now you can interpret this power. How you can interpret that? Per second, it will emit P amount of energy, or you can say yes, P amount of energy. So how you can interpret this power in terms of energy, and when we will interpret that in that way, then we can understand that how actually we can get that dNp by dt. So what does P watt means? That P amount of energy coming, or you can say you may write that it is just or coming from source directly. Coming from source per second, per second. Okay, so P amount of energy of light, the amount of light energy is coming from source per second. Okay, now we will define. Now, so we can write dNp by dt as P over E. I think you may have a little confusion, so let me clarify you with an example, simple example. Suppose that source has energy or is emitting a light source of energy 30 electron volt. Okay, and each photon each photon carries its own energy, and that is observed, or you can say we have reported that energy of that photon be suppose 5 electron volt. How many photons will be coming? 30 over 5, 6. As simple as that. What we have done, 30 was the, we have defined in terms of energy, but actually it was 30 watt. It was 30 joules of 30 electron volt of energy per second. So it is power over E. Fine. Now I think you know, or we can define intensity. Intensity of light is given by power per unit cross sectional area. Okay, so P will be is equals to I into A. Okay, now we can write IA over HC over lambda as energy. You can write in terms of wavelength. You can write in terms of frequency also. Both are correct. No issues at all. Now, in our previous session, we said that this intensity is actually directly proportional to number of photon. How it is, we will here also see it through formula. So let's just arrange this particular formula. dNp by dt is what? Your Ia lambda over hc, or you can say Ia over h into nu. Nu is the frequency. Now you can see this is number of photons per unit time. This is your intensity. So you can say here that number of photons actually corresponds to, or you can say directly proportional to the intensity of incident light. Fine. This is the, you can say, essence of number of photons. Fine. Okay. So this is your concept of number of photons uh, per unit time. Okay. Fine. So now we will discuss on that particular topic, that is maximum kinetic energy. Okay, we'll just find a formula for that also. So we will discuss a term again, stopping potential. We have just introduced this term in between only, but it is important to understand this to get that formula for kinetic energy maximum. So it is actually the minimum retarding potential, as it is named, as name suggests, stopping potential, minimum retarding potential to stop photoelectric emission, and it is denoted by V naught, not mu naught, it is V naught. Okay, that is stopping potential. There is a minimum retarding potential that is required to stop photoelectric emission. Now, from the basics of electrostatics, you can say that maximum kinetic energy, or you can say work done, is charge into potential, and here that potential will be stopping potential. And when we are concerned in photoelectric, this is a general formula. Q into V is general formula. V naught we have just specified here, stop in terms of stopping potential. Now when we are concerned in your photoelectric effect, then we will use this Q as E into V naught. But again, this E is not actually, it is minus E. We will write this K max more mathematically as mod of K max is equals to EV naught. E is the electronic charge. Okay, it is actually minus 1.6 into that 10 power minus 19, I think, right? But here we will use mod to just make this particular quantity positive, EV naught. Okay, now we will just write that formula, whole photoelectric equation which we have discussed in terms of all the parameters which we have inculcated. Fine, let's discuss. And now we are on the verge of completion of this particular topic, but there is nearly 5 to 10 minutes are left to complete. That will be EV naught. Again, I'm writing firstly the equation, okay, otherwise you may get confused. So see, K maximum is equals to H nu minus phi. We wrote it as H into mu minus nu naught. We can write it as E into V naught, or we can write it as E into V naught HC into 1 by lambda minus 1 by lambda naught. Right? This can be done. Again, what you can write, V naught is equals to H by E, H naught by. Is it correct or not? Just check. You can check. Check on this. Uh, okay, you can check this, or I need to check. Just EV naught is equals to H nu minus H5. See, again I am writing. You can write it as H into nu minus nu naught, right? And here by E, and that is stopping potential. Now we will plot a graph between stopping potential, this and this. So what will be this? Like this. You can write as H by E minus nu naught, or you can write as H nu by E minus H nu naught by E, and this is your on y-axis, this is in your x-axis, so it is actually the y is equal to mx minus. Okay, graph is very uh, good. The slope is positive but intercept is negative. You can draw like this, and here it is dotted, and this will be your h by nu, h nu naught by. Wait. Yes. Okay. This is your theta. This frequency is your nu naught frequency. Okay. This frequency is your nu naught frequency. Fine. Yeah. This frequency is nu naught frequency, means this is the minimum amount of frequency required for the photoelectric emission. See, from till this kinetic energy maximum is 0, as V naught is 0, but then suddenly it can say gradually it's increased with a slope, this theta. So we can write slope here as tan theta, and that tan theta will be h over E, and that is constant actually. That tan theta slope is constant actually. Fine, because h and E are both are the constants, but that will be constant value. The slope is constant, uniform, we are getting uniform graph, no issues at all. So this was the plot of V naught and frequency. Now again, you have to see this formula and just see here, work function is constant for a particular metal. Okay, for a particular metal, work function is constant, and this h by E is also constant. So we can write this stopping potential depends on frequency of incidental light. Stopping potential. This stopping potential depends on is directly proportional on the frequency of incidental light. Okay, so just try to absorb this. Fine, I think it is fine. Okay, now we will conclude it with the 2 points. Okay, one more thing, saturation current. It is not a new term. Okay, saturation current is not a new term. It's the same photo current, but it is its maximum value. So maximum value of photo current. This saturation current is actually, we write it by IS. That is actually depends on the intensity of, you can say, incidental light. That is equals to directly proportional to number of photons. So if you increase the number of photons, then saturation current will increase. So let's conclude with that 2 points. So two important conclusions. What are these two important conclusions? First, stopping potential, tell me, depends on frequency, depends on intensity. Which one is correct? This is correct, this is wrong, and always you have to remember this. Stopping potential is actually dependent on frequency, not on intensity. Okay, don't get confused. It's a very important point in quantum physics. Actually, in the, you can say, conclusion part of your, what you say, photoelectric effect experiment. Okay, the stopping potential is dependent on the frequency of incidental light, rather not on the intensity. Fine. Second point, saturation current. Saturation current, does it depends on frequency or it depends on intensity? But I'm saying intensity, it means number of photons. It directly goes to number of photons we discussed, not on frequency but on intensity for sure. Okay, so you might get confused. So these are the 2 points which you must note it out. Okay, so these are the two things. One is stopping potential dependency, and one the dependency of your saturation current. Okay, now I don't think there is a need of saying that, but still I am saying that this particular photoelectric effect was meant to show the particle nature or ray nature of light, because we have discussed in terms of photon, not in terms of wave. So let's conclude it with a line that photoelectric effect, photoelectric effect proves the light light's particle, or you say ray nature. Photoelectric effect proves the light's particle or ray nature. Okay, so this is the thing. I hope it is clear to you. Photoelectric effect proves the light's particle, or you can say the ray nature. Okay, it is not associated with any of the concepts of wave and all. Photoelectric effect is uh, just solely on the, you can say, particle nature or ray nature of light. Fine. Okay, so yes, so this was our today's lecture, and with this we are completing today's lecture. In next lecture, we will discuss, I think, Compton effect. That is again a very important effect that will tell us about the existence of photon. We are discussing that photon experiment. We have even done the experiment with photon, but its existence, we will get to know through the Compton effect, which is again by a scientist, I think Arthur Compton. Okay, Arthur Compton, and this was by Albert Einstein. I think everyone knows, and he also got Nobel Prize for this. I don't remember exact year, but in obviously 20th century only, in the early 20th century, in 1920, 30, near to that. Okay, so this was his contribution in. So I said, as quantum physics is a very big university, there are many scientists who have contributed to this. So Albert Einstein is one of them. And then in next class we will have the introduction to Compton effect, in which Arthur Compton has given his contribution to the quantum physics. Fine. Okay. So do revise this. Okay. So thank you so much for joining me in this session. In next session we will discuss Compton effect. In next lecture. Till then, bye bye. Take care, and I'm exiting. 1, 2, 3, and this lecture will be on 15th of wait, I'm just 11, 16, 15, yes, 15th of May 2026, 4 p.m. I guess. Fine. Okay, thank you.